Hello everyone, today we will introduce the stress analysis about the rigid pavements. We will spend 2 lectures to finish this topic. First, let's have a quick review about the rigid pavement. Usually the rigid pavement is constructed with some PCC slabs, and the thickness of the slab is usually smaller than the asphalt layers in the flexible pavement. In the construction, the slab is placed on top of the sub-base course. Also, the slab will usually have a very high elastic modulus, which can help the pavement to support a very high load carrying capacity. In addition, for the analysis of the stress and strain for the rigid pavement, we will use the beam action for the PCC slabs. Finally, there are many sources about the stress applied for the rigid pavement. We will usually consider the traffic loading, moisture and temperature changes, and the differences over the slab cross-section. The details about these sources will be introduced in the future lectures. The differences between the rigid and the flexible pavements are very obvious. In the rigid pavement, the PCC slabs has a much higher stiffness than the asphalt concrete in the flexible pavement. In that sense, for the rigid pavement, the surface layer provides more load resistance, and the underlying layer are not quite important for the rigid pavement. In addition, the rigid pavement is usually not continuous, and we have to apply some joints for the PCC slabs during the construction. This kind of discontinuity is one kind of dominant features of the rigid pavement. Finally, the environmental factors plays a very important role for the analysis of the stress in the rigid pavement. For example, the temperature will usually cause some curling effect for the pavement, while the moisture will generate a warping effect. There are some common distresses applied for the rigid pavements, such as the corner breaks, where the cracks intersect adjacent transverse and longitudinal joints at an approximately 45 degree with the direction of the traffic. In our previous lectures, we also introduced the mud pumping and the punch-out distresses applied for the rigid pavements. In the stress analysis for the rigid pavement, we will focus on 4 major factors, including the traffic loads, cyclic changes in temperatures, which will introduce warping, curling, shrinkage, expansion, and contraction effects, changes in moisture, and volumetric changes in the base and sub-base courses. Also, there are some other factors which will also affect the result of the stress analysis, such as the permanent deformation of the supporting media, the cracked slabs. However, the analysis of this factor is very complicated. In this class, we will just skip this part. The traffic load will usually cause the bending effect to the PCC slab, while the tension will usually be applied at the bottom of the slab. The impact of the temperature and moisture are very similar. They will cause the curling and warping stresses where the tensions will be applied at the different depths of the slab. The impact of the volumetric changes is also quite straightforward. If the volume increases, it will cause some compression to the slab, while if the volume decreases, the tension will be applied to the slab. There are some common distresses caused by the traffic load for the rigid pavement, such as the fatigue cracking, including bottom-up and top-down cracking, joint faulting for endowed JPCP, and punch-outs for CRCP. For the distress related to the temperature, we will have the low temperature mid-slab cracking and high temperature joint or crack distress, while the moisture will usually cause some mud pumping and D-shaped cracking. In this page, the figure on top shows the fatigue cracking caused by the traffic load. Usually for the PCC slab, the tensile stress is maximized at the bottom of the slab and is usually located at the middle point of the wheel. In that sense, it will cause the bottom-up fatigue cracking. The figure at the bottom shows the generation about the mud pumping and faulting caused by the moisture and the traffic load. We have already introduced the mechanism of the mud pumping in our previous lectures. The figure here shows the generation of punch-out, which is related to both longitudinal and transverse cracks. The moisture also causes some de-cracking, which has closely spaced crescent-shaped airline cracking pattern. This kind of cracking usually occurs at joints, cracks, or free edges. Now we can analyze the stress and strain for the rigid pavements. But first of all, we need to define the assumptions for the analysis. For the rigid pavement, we know that it consists of the PCC slabs and some unbound layers such as base and subgrade layers. For the PCC slabs, we assume that they are linearly elastic and linearly thermoelastic, while for the unbound layers, we assume that they are linearly elastic. At the same time, they will perform as the Winkler spring as shown in the figure on the right. This is actually one of the most different assumptions from the flexible pavement, and it will make the analysis about the stress and strain very different from the flexible pavement. In the analysis of the stress for the rigid pavement, one of the most important variables we have to consider is the coefficient or modulus of the subgrade reaction. This modulus has been introduced in the previous lecture for the soil property. Basically, the value of K is defined as the ratio between the reactive pressure applied to the PCC slab and the measured maximum deflection of that slab. Generally, the modulus of the subgrade reaction is applied to evaluate the in-situ stiffness of the subbase or subgrade layers. The value of the modulus can be estimated from the plate load test, which is shown in the figure below. In this test, we will set a plate with a diameter of 30 inches or 750 millimeters, and then we measure the deflection of the load during the test. With the measured deflection and the applied load, we can then estimate the modulus by this equation as P over delta. Based on analysis about the stress and strain of the rigid plate in the flexible pavement analysis, we can find that the distribution of the pressure about the rigid plate is not uniform, and the distribution can be shown in this equation, where it's determined by the distance of the point to the center of the contact area. Here, little p is the average contact pressure, and A is the radius of the contact area. Also, we can find out the value of the deflection at point A, where A is located at the center line of the contact area and it's located at the bottom of the rigid plate. And this equation shows the estimation of the deflection at point A, which is also identified as the maximum deflection caused by the load applied to the rigid plate. Then, based on the definition of the modulus of subgrade reaction, we can identify the modulus as the contact pressure over the maximum deflection, which will give you the value as 2 times E divided by pi times 1 minus mu squared times A. And this figure shows the relationship between the modulus of the subgrade reaction and the modulus of elasticity. In the summary, we know that the modulus of the subgrade reaction is not a fundamental soil property, so it's not easy for us to measure the value of K. Also, the value of K depends on a lot of factors such as the width and the shape of the loaded area, position within the slab, and times, which is related to the portion of the fine-grained soils. In reality, we will usually introduce the plate load test to identify the approximate value of K, which is also the function of the plate size. The table here summarizes some typical values of the modulus of subgrade reaction. Basically, with a higher value of the fine-grained soils, the value of the modulus will be larger. As we stated previously, we will apply the beam reaction for the analysis of the stress in the PCC slab. The page here reviews the beam equations, where we will have the bending moment defined as minus EI times the second order derivative of the deflection W and location X. We also have the shear force as minus dm over dx and external load Q equal to dq over dx. By combining these three equations, we can find out the equation to identify the relationship between the deflection and the load applied to the beam. In the rigid pavement, the PCC slab is placed above the base or subgrade layer, and we also assume that these unbound layers will perform as Winkler springs. In addition, from our previous analysis, we can see that the deflection behind the PCC slab is a constant, which we define as the variable of W. Then, based on the beam equation and the support from the unbound layer, we can identify the relationship between the deflection and external load Q in this equation. Here, E times I is defined as the sectional stiffness, and Q is the distributed load, K is the coefficient of the subgrade reaction. In reality, the PCC slab is placed on a battle spring, which is in a two-dimensional space. This indicates that we have to consider the distribution of the deflection and the distributed load in both x and y coordinates. And the equation here shows the relationship between the deflection angle and the distributed load in two-dimensional space. In this equation, capital D is the bending stiffness, which is defined by the equation here. In this formula is not a slab thickness. While for the definition of the bending stiffness, we have the variable h, which is the thickness of the PCC slab. And capital E is the modulus of elasticity, mu is the Poisson's ratio. If the dimension of the PCC slab is infinite, then we can find out the analytical solution for the deflection. The equation here shows the distribution of the deflection in the infinite rigid slab. It's defined as a function of r. Here, r is the distance from the point, say any point, that we want to estimate to the center of the load. Also, there's a function z3, which is a special mass function to identify the deflection. In this equation, we also have one variable L. The variable L is defined by the equation here, where L is the function of the thickness of the PCC slab and the modulus of the subgrade reaction. We also define a new variable beta, which is set as 1 over L. In this equation, L is actually applied to measure the relative stiffness of the slab to the foundation. Also, for the analysis about the deflection, we will only consider the points with the distance from the point to the center of the pressure less than 5L or less than 5 over beta. For the points which are out of this region, we will discard the impact from this load. In addition to traffic load, the temperature also plays an important role in the stress analysis of the rigid pavement, usually due to the temperature gradient between the top and bottom of the PCC slab. We will observe the curling effect. The two figures below shows the curling effect at day and night time for the rigid pavement. At daytime, you can see that the temperature at the surface of the rigid pavement is higher than that at the bottom. In that sense, due to the expansion of the slab on the surface, you will see that the slab will be expanded upwards, while at night, the temperature at the surface is usually less than that at the bottom. Then, the slab will be shrunken downwards. The magnitude of the curling stresses usually depends on the slab property, including the thickness, Poisson's ratio, and slab strength. It's also related to the support conditions and magnitude of the temperature difference at top and bottom. For daytime cooling, we can observe compressive stress at the top and tensile stress at the bottom. With that, we can see that it's very critical when the load is applied at the center of the PCC slab. It also indicates that it can easily cause the distress for the PCC slab when the load is applied at the center. While for the nighttime cooling, the tensile stress is applied at the top and the compressive stress is applied at the bottom. We will observe that it's very critical when the load is applied at the corners. The impact of the temperature can be analyzed with the thermal strain, which is defined as epsilon equal to alpha times delta T. Here, alpha is the coefficient of the thermal expansion and delta T is the temperature difference at the top and bottom of the slab. Usually for the PCC slab, the thermal strain is restrained by the thermal stress, which is determined by the slab stiffness and foundation stiffness. If the dimension of the PCC slab is infinite, then we can assume that the thermal strain can be totally restrained by the thermal stress. With that, we can estimate the x-directional stress due to the bending in x and y directions. The first equation shows the extreme fiber x-direction stress due to the bending in x direction. In this equation, we will have E as the modulus of elasticity, alpha as the coefficient of the thermal expansion, delta T is the temperature difference at top and bottom of the PCC slab, and V is the Poisson's ratio. The second equation shows the x-direction stress due to the bending in y direction. With these two equations, we can then find out the combined x-direction curling stress at the extreme fiber as the equation here, which is E times alpha times delta T over 2 times 1 minus V. If the dimension of the slab is finite, for example, if we consider the slab with the length of Lx and the width of Ly, then we can estimate the thermal stresses for x and y directions based on the two equations here. And we can also estimate the value of L. In this equation, Cx and Cy represents the correction factors for the finite slab effect and usually is set as the value smaller than 1. The figure here shows the relationship between the constant coefficients Cx and Cy with respect to the length or width of the PCC slab. The horizontal axis is L over little l. Here, little l is the radius of the relative stiffness, which is defined in the previous page. And C will be applied for both x and y direction, depending on the width and length selected for the horizontal axis. In the rigid pavement design, we will usually consider some typical temperature gradients. Usually, the typical maximum temperature gradients varies from 2.5 to 3.5 Fahrenheit per inch, or is equivalent to 0.055 to 0.077 Celsius per millimeter during the daytime, and at night, the maximum value will be approximately half of the range at the daytime. However, for the real project, you need to conduct some field measurement to get a precise estimation about the temperature gradients. Now let's check one example for the estimation of the thermal stress with a finite slab. The figure here shows a concrete slab with the length of 25 feet, width of 12 feet, and thickness of 8 inches. The temperature difference at top and bottom is 20 degrees Fahrenheit. We assume that K equal to 200 psi, alpha T equal to 5 times 10 to the power of -6 inch per degree. And we want to find out the maximum curling stress of the slab. To solve this problem, we first need to estimate the values of two coefficients, capital Cx and Cy, which can be obtained from the figure on the right. In this figure, we need to find out the value of L over little l to identify the values of these two coefficients. Here, Letter L is the radius of the relative stiffness, which is defined as E times h cubed divided by 12 times 1 minus v squared times k to the power of 0.25. For the concrete slab, we will have E as 4 times 10 to the power of 6, and the thickness is 8 inches divided by 12 times the value of the Poisson's ratio is 0.15 square times the value of K as 200. With that, we find out the value of L as 30.57 inches. Then we can find out the value for the length, which would be the value of Cx. First, we need to identify the value of Lx. In this case, it's 300 inches divided by letter L. That is 9.81. And from the figure, we can then derive the value of Cx as 1.07. Similarly, we can find out the value for Cy with the width the value is 471, which will give you the value of Cy as 0.63. And then if we go to check the maximum curling stress at x and y directions, you can see that the maximum value falls at the x direction. With that, we can just calculate the curling stress at the x direction. That is sigma x equal to E times alpha times delta t divided by 2 times 1 minus v squared times Cx plus v times Cy. So that is 4 times 10 to the power 6 times alpha is 5 times 10 to the power of minus 6 times the temperature difference as 20 divided by 2 times 1 minus 0.15 square times Cx is 1.07 plus 0.15 times 0.63. This will give you the value as 238 psi. So that's the solution for this problem. You can also use the similar formula to find out the stress at y directions and make a comparison to make sure that sigma x is also the true maximum curling stress as what we specified. So that's all about lecture today. Thank you very much for your attention. In the next lecture, we will finish the rest contents in the stress analysis for the rigid pavement.